Hi, it's Carly McAvoy. I wanted to talk about correlation today. The linear correlation coefficient, R, is a number that measures how well the graph of paired data fit in a straight line. It shows the strength and the direction of the linear association between two quantitative variables, quantitative just meaning variables that have numbers. So a correlation coefficient which are close to -1 or +1 have the strongest correlation. And the values close to 0 indicate a very weak or no correlation. So in pictures, what this looks like, if you had a correlation coefficient of -1, exactly -1, you would have a line that falls from left to right that actually makes a line. Over here, if it's +1, it rises from left to right, making a straight line. In the middle, 0, it's just a blob of points, and you can't really tell whether there's an association or not. Two things that are not associated, they're not dependent upon each other. If they do have an association, positive or negative, they're dependent upon each other. One thing can cause the other one to change. And if you had something like -0.7, you'd see it going from left to right, down from left to right, but you'd also see that it doesn't make a perfect line, but it kind of does suggest a line, and even -0.4 suggests somewhat of a downward trend, whereas 0.3 suggests an upward trend, and then it really just when you have 0 is when you really can't see any trend at all. A correlation between two variables exists when one of the variables, the values of one variable are somehow associated with the values of the other variable. And when that correlation exists and the plotted points approximate a straight line, there is a linear correlation. Linear meaning a line. So the correlation coefficient has no units. It's between -1 and 1. It's designed to measure a linear relationship, and there are different relationships, but we're just looking at linear. The scaling the data has no effect. The order of the data does not affect R, and I'll talk about that in a minute. And the order of the variables has no effect on R, and both variables have to be quantitative. So a correlation coefficient is not resistant to outliers. But what does this mean, the order of the data and the order of the variables? Let's take a look at a graph that I have up in GeoGebra. And here's two things. What we're looking at is cigarettes per day, which on the x-axis, and life expectancy in years on the y-axis. And I have this data. You can see I have 5, 23, 25, 48. I don't have these ordered from least to greatest. If I did order that, or if I changed the order of the data values, it would not change my R. R is shown up here to be -0.7134. That doesn't change if I order this data differently, as long as my pairs are consistently matched. So 5 is matched to 80, and etc. Over here in GeoGebra, you can change that so that we're looking at the B variable on the x-axis. And if I did that, you can look up here and see what R is. R is still -0.1734. So it didn't change if we change the order of the variables, or if we change the order of the data values, doesn't change it. What does change is the slope of the model when you change that. So remember, slope is not the same as a correlation coefficient. In this case, our slope is -0.81. That is when our B column was on the x-axis, and our R was -0.7134. So the signs are the same. They're both negative, but the values are different. And so if we change that back, and we see that we didn't change the R, but now instead of 0.81, we have -0.63. So again, that they're both negative. That what you would expect. But the values are different. Those are two different things telling us different things about our data. Okay, so coming back over here, we have explanatory variable is the X, or the independent variable. And for our example that we're going to look at even further that we just saw on GeoGebra, the cigarette smoke per day is our independent variable, or our explanatory variable. So we should put that on the x-axis, because the number of cigarettes that you smoke per day could explain your life expectancy, right? Or it's dependent upon that anyway. They are correlated, and we can look to see whether they're positive or negatively correlated. And the response variable is the life expectancy in years. So when I look at that, this is back a screenshot from that GeoGebra stuff we were looking at. We saw R is -0.7134. that is that correlation coefficient. We know then that that's going to be negative as dropping from left to right as we go. And negative 7.71 is not 1, but it's a pretty strong correlation. What is r squared? Because you're going to be asked that too. R squared is the coefficient of determination. And what that tells you is really how effective is your model, or what's the strength of your model. And if you have a correlation of 0.509, that means that 50.9% of your points should fall within the regression line. And we kind of explains what percentage of the values are explained by your coefficient. So in this case, I have these labeled as cigarettes per day and life expectancy, and we have this dropping line, and you can see that we have the slope of negative 0.063, and then the correlation coefficient is similar in sign, but it's also different in value. And then what does this 85.72 mean? Well, 85.72 is the starting point. In other words, if you didn't smoke any cigarettes, what would your life expectancy be, right? And then the slope tells us that it's going down because it's negative. So it's kind of the rate of change as you do that. If you're in GeoGebra, this is really hard to see. I wasn't really going to talk about this, but you can also put in, like I put in this case, 7. And that means, what if I smoke 7 cigarettes, hit enter, then what would my life expectancy be? So you can use GeoGebra to predict from your model. And that's called interpolation, when you're asking questions that are within your data value. 7 is within your data value. If you go outside of that and extrapolation, then you, like, let's say, okay, what if I smoked 60 cigarettes a day? Well, we don't really know how the model would hold up outside of that. So you want to be careful going outside the range of your data values when you're asking those questions. If you didn't have GeoGebra, then you could use this formula to find R, or if you didn't have a calculator, and you could figure out what these symbols mean, and you could do that yourself. But luckily, we're not doing that, and you're just glad that you're taking statistics in the 21st century, and we have technology to do that for us. And finally, the last thing I want to tell you is that correlation does not imply causation. The example you'll see around is the rates of violent crime in ice cream sales have been shown to have a strong correlation. Should we then conclude that ice cream sales cause violent crime? Should cities ban the sale of ice cream? And the answer is that there's some other lurking variable that's probably causing this. And in this case, it's just warm temperatures. When it's nice outside, people go outside, they hang out, they buy ice cream because it's hot, and then people get victimized because they're out and about. If you're home and if it's home in the middle of the winter and everybody's shut up in their house, there's not as much likelihood of you being attacked or having violent crime committed against you. So they are correlated, but there's not a causation, right? And so if you also wanted to see how to use GeoGebra to create a scatter plot and find that correlation coefficient, there's a video link here. I'll also put that in the link in the video description on YouTube for those of you who don't have the document in front of you. All right, have a fantastic day, and we'll talk to you next time.